Okay. Hello, can you hear me in the back? All, can you hear me? Great. It's 10 o'clock. Welcome, everyone. Welcome to Oxford to Symmetries 2024. We called it 2024 because we hope there will be a 25, 26, and so on in anticipation. It's great to see so many people from different backgrounds, high energy theory, condensed matter, high energy phenomenology also, and mathematics, to come here to Oxford and to discuss everything related to generalized non-invertible categorical symmetries. I am really sorry about the weather. I'm sure you all thought that coming to Oxford, it will surely be raining. We have probably sunshine and heat. Hopefully it'll be still a pleasant experience for you here. Okay, so we'll have talks. We try to not have too many long talks. We have 25 plus 5-minute talks, and we'd actually like to have lots of discussions. And so there are lots of time in the breaks to discuss. There'll be a poster session and a gong show today at the end. You already see the posters out there. And we have a conference dinner on Wednesday. And if your name tag has a WADM logo here, you're signed up for the dinner. If you believe you should be signed up for the dinner and it doesn't have this, you need to see one of the organizers, please. Okay? Great. So I think this is all from me. We'll now turn to Yunqin, who's the first speaker. We are recording, by the way, all the talks. There's no Zoom link. So all questions should be posed through the microphone so we can actually hear them also on the recording, please. This one? Try to put it in the middle.
Good.
And you need to speak into it, and in fact, when if you are pointing this way, it's better to have it attached. Anyway.
Can I just hold it? Maybe it's easier.
Okay, you can also do that.
Okay, yeah, I have two hands.
Okay, so the first speaker is Yunqin Zheng from YTP Stony Brook, and he'll speak about symmetry TFTs, boundaries, and non-invertible symmetries resolved Affleck-Ludwig-Hardy formula. Okay. Anyway. Yeah, it will materialize, yes.
Okay. So I'd like to begin by thanking organizers for giving me the chance to speak. So today I'm going to talk about the symmetry TFT boundaries and an application to non-invertible symmetry resolved Affleck-Ludwig-Hardy formula. This talk is based on work in joint collaboration with two amazing collaborators. Okay, so Choi and Brandon Rihan, both are in Stony Brook. And okay, let me get started. So first of all, the notion of the generalized global symmetry has recently been extended. That's been past a decade. Recent years, people have studied a lot of aspects of the generalized global symmetries. For example, anomalies, the generalized charges, the incompatibility with the boundary conditions, and how to gauge in the non-invertible symmetries. And along the way, the sandwich construction turned out to be recognized as a very beautiful tool to extract the various aspects of the generalized symmetry. For example, they are very useful to extract the symmetry-related kinematic aspects of the quantum field theories. And by the way, in this talk, I'm going to focus on the 1+1D quantum field theory. And for simplicity, I'm going to focus on the CFTs. So what does the sandwich construction do? So we first start with the 1+1D CFT Q with non-invertible symmetry described by the fusion category C. And then what sandwich construction tells us that the system can be expanded into a triplet, where in the middle, which is we have 1D topological quantum field theory called the Symmetry TFT, whose lines are given by the Dream field center for the input fusion category C. And on the left-hand side, we have the topological boundary condition, where the symmetry lines can live on the boundary conditions. And on the right-hand side, we have the non-topological or dynamical boundary condition, which encodes all dynamical informations of the quantum field theory. So the nice thing about this sandwich construction is that everything to the left, in the middle and to the left of the diagram are topological, and everything. So the dynamical aspects of the series are all localized on the right-hand side. Okay. So we study the sandwich construction not only because it's beautiful and convenient, but sometimes in certain problems it's very difficult to make progress without using the sandwich construction. Two of such problems are involved the anomalies of the non-invertible symmetries, especially dimensions, and also the representation of the non-invertible symmetries.
If you're holding it, then you need to hold this one. But it would be better if you would attach it. Let me attach it. All right, so let's try it here.
Is it better now?
Yeah, it's better.
Yeah, the second problem is the representation of the non-invertible symmetries carried by a local operator, paired by the bulk operators, which can be both local and non-local. In this talk, I'm going to put more meat on the second bullet point, which is the representation of the non-invertible symmetries carried by the boundaries and the boundary changing operators. As we are going to see, that the sandwich construction will provide us some bonus of understanding the physics at the boundaries and the boundary changing operators. Okay, so how do we understand the boundary conditions using the sandwich construction? So we started with our theory Q, and it has the boundary M, bigger M. And if we blow it up into a 2+1D sandwich, the sandwich cannot go all the way up. It has to be truncated somewhere in the top. But because the law of the sandwich construction is that we need to we demand that everything in the middle and on the left part of the figure must be topological. So the boundary condition at the top must also be topological as well. Therefore, it's calcified by because the topological boundary conditions of the topological field theory is calcified in 2+1D. Also, the boundary changing operator, M, little m, between the two topological boundary conditions is also topological. So in short, the boundary condition of the 1+1D CFT can be expanded also into a triplet. Little m and little capital B, both are topological, and this boundary changing condition, m tilde, is in general non-topological. So what do these three pieces of data mean? So in order to understand it, let's first ask the question of how does the symmetry act on the boundary conditions? So it's well known that the conformal boundary conditions of the CFT form a non-integer matrix representation, in short NIMREP, under the parallel fusion of the symmetry operator in the symmetry category. What does it mean? So it means that we have a symmetry operator A, and we bring parallel to the boundary condition. Then the resulting boundary condition can be expanded into a direct sum of the simple boundary conditions weighted by the non-negative integers. So after we blow it up into a sandwich, then because the symmetry operator only lives on the topological boundary, then if it parallelly fuse the symmetry operator to the top, then it only changes the boundary changing condition. So the boundary changing condition, little m, form the same NIMREP under the parallel fusion of the symmetry category C. And the different boundary changing conditions that are related to each other by fusing the symmetry operator form a multiplet. And so this is the boundary changing line operator. But also, we note that the top topological boundary condition is invariant, is not changed under the parallel fusion of the symmetry operator. Therefore, it labels, give the NIMREP a label of the
give indirect label and also labels the multiplets of the boundary changing operator related by the symmetry action. Okay. So in order to understand these abstract things, let's consider a simple example. So we consider the Ising CFT, and for now, let's only focus on the Z2 symmetry. So it's well known that the Ising CFT has three conformal boundary conditions, simple conformal boundary conditions, and these three simple boundary conditions form two multiplets. One is the Z2 singlet, and the other is the Z2 symmetry breaking doublet. And how to understand it in the sandwich picture? So the Ising CFT, first of all, it can be expanded into a triplet, where in the middle we have a Z2 gauge theory. And the Z2 gauge theory is well known to have two topological boundary conditions, Dirichlet and Neumann. And on the left-hand side, we have the Dirichlet boundary condition on which the symmetry generator can live on. So I'll denote the symmetry generator as eta. And let's further understand how the three boundary conditions can be organized according to this sandwich construction. So to begin with, let's start with the second and the third picture, where on the top we have a Dirichlet boundary condition. Because the top boundary condition and the symmetry boundary condition are the same, so the boundary changing operator are just the lines that live on the Dirichlet boundary condition, which can either be the identity or the symmetry operator eta. So, and it's clear that under parallel fusion with another eta line with this boundary changing operator, then the two boundary changing operators are swapped to each other. And this is precisely how these two boundary conditions form a Z2 symmetry breaking doublet. On the other hand, if we put a Neumann boundary condition on the top, then it's well known that the boundary changing operators between the Neumann and the Dirichlet boundary condition are the Kreimas-Wannier duality interface. And the one remarkable property of the Kreimas-Wannier duality interface is that it can absorb the Z2 symmetry line eta under parallel fusion. Therefore, it defines the Z2 preserving boundary condition, so which is the free boundary condition denoted here. Okay, so far for the boundary conditions. Let's proceed to talk about the boundary changing operators. So the boundary changing operator can be constructed by starting with two boundary conditions, and we put them adjacent to each other. So I'm going to denote the boundary changing operator as V. And in the CFT, we can use the state operator correspondence. And under state operator correspondence, the local operator V, which is the boundary changing operator, is mapped to a state in the Hilbert space on the interval. And the boundary conditions out of the interval are also the M1 and the M2s. Now we want to understand how the non-invertible symmetry acts on the boundary changing operator or acts on the state on the interval. So the non-invertible symmetry acts on the boundary changing operator via the so-called boundary lasso action. So what is the boundary lasso action? So we start with the boundary changing operator, V, which connects the M1 and the M2, so two boundary conditions. And then we put an open topological line that terminates at the J1 and the J2. And in general, J1 and the J1 will connect the two different boundary conditions at the boundary, so M1 and M1 prime, and J2 will also do the same. So now the boundary lasso action just means that we bring the J1 and the J2 very close to the V and fuse them together, and which will define another boundary changing operator V prime on the right-hand side of the figure. Remarkably, the V and V prime are of different types. V is connecting the M1 and M2, and V prime is connecting M1 prime and M2 prime. So different these open topological segments labeled by J1, J2, and A can fuse with each other, and the algebra formed by them defines the boundary tube algebra. So this boundary lasso action should remind us the ordinary lasso action in the bulk, which was discussed very nicely in this paper. And in particular, it's well known from this paper that the bulk lasso action will also change the type of the local operators, and in particular, can map the genuine local operator to a defect local operator. And we find the similar thing here. So under the state operator correspondence, the lasso action can also be understood in this interval picture, where the topological line that connects between the two boundaries, well, in general maps the state in one Hilbert space labeled by the boundary condition M1 and M2 to another state in another Hilbert space labeled by boundary condition M1 prime and M2 prime. So in order for the boundary tube algebra to act closely on a Hilbert space, we need to consider the extended interval Hilbert space, where we need to sum over all the possible boundary conditions. Okay. Now, how to understand the boundary changing operator in the sandwich picture? So we started with two boundary conditions. As we mentioned earlier, they can be expanded into two triplets. And then the boundary changing operator is also naturally expanded into a triplet, where in the middle, we have the alpha line, which is the topological boundary changing line between the two topological boundary conditions, B1 and B2. And now, all together, we have three topological boundary changing line operators, M1, M2, and alpha. And they meet together at the junction V, which is also topological. Okay. Wait. I think there is some bug in the slide.
One slide. This is not here, so this.
Oh, can I switch to my computer for the moment?
Yeah, okay.
It's just one slide missing, right?
Sorry?
It's one slide that's missing.
Maybe a couple of slides. Maybe.
Go back, it was 9 and there's...
Yeah, there are two slides are missing. How do
Windows access.
Let's see.
So I have to change here.
Just a map. Okay, cool.
Then put it on.
Very nice. Okay, so, okay, let me just do it here. Maybe you can see the cursor better here. Okay, so we have discussed how to understand the boundary changing operator in the sandwich construction. And now let's understand how the boundary lasso action acts on the boundary changing operator, in the sandwich construction. So as we discussed, which is obvious from this figure that the boundary lasso action only changes the topological boundary changing operators, which are labeled by little m's, and the topological boundary junctions, which is denoted by little v. So which means that everything in the middle are unchanged under the boundary lasso action. And this means that alpha, which is the topological boundary changing operator, is invariant under the boundary lasso action. Therefore, it labels the representation of the boundary tube algebra. And under the state operator correspondence, this alpha also labels the irreducible representation of the algebra on open topological lines acting on the interval. Okay. So far we discussed so far we used the sandwich construction to discuss the representation of the non-invertible symmetries that acts on the boundary conditions and the boundary changing operators. And we already see some bonus that the sandwich construction brought us. In particular, from the sandwich construction, we know that the boundary condition, topological boundary conditions on the top labels the nim-rep of when the non-invertible symmetry acts on the boundary conditions. And the boundary changing operator alpha labels the irreducible representation of the boundary tube algebra acting on the boundary changing operators. Okay, so far we discussed the formal stuffs. Now let me briefly mention an example, an application of what I discussed above, which is I'm going to use the machinery that we discussed to calculate the non-invertible symmetry of the Affleck-Ludwig-Cardy formula. So what is the Affleck-Ludwig-Cardy formula? So in the early 90s, Affleck and Ludwig, who extended the result of the Cardy, found the universal high temperature limit of the CIT partition function when space is interval. And with the two boundary conditions labeled by M1 and M2. And they found the universal behavior function, which receives the contribution of the boundary G functions. And also, there is an exponential part, which is controlled by the bulk central charge. Later, last year, Kuzuki, Muriciano, Uguri, and Pao consider a more refined version of this formula by adding the global symmetries. In particular, they discussed the ordinary invertible global symmetries. And they asked, what is the behavior of the partition function when we restrict to the Hilbert space with the fixed representation? And this is the answer they find. So on top of the original Affleck-Ludwig-Cardy formula, they found an additional contribution, which is controlled by the representation. This little d alpha is the dimension of the representation, and the denominator is the volume of the symmetry group. So in this talk, I'm going to extend their result to the case of the non-invertible symmetries. So I should mention that this line of development is very closely related to a parallel discussion where we consider the partition function not on the interval, but on a circle. And these are the very nice works that appeared recently. Okay. We are also inspired by their. Okay, so let me first briefly review what the Affleck-Ludwig-Cardy formula is. So Affleck-Ludwig-Cardy formula computes the analysis partition function in the high temperature limit. In other words, we consider this Q goes to 1 in the open string channel. So we have the boundary conditions, and the Hilbert space is an interval, and we can partition function by taking a trace of the states in the interval Hilbert space weighted by this standard factor. The key trick to compute this partition function is to use the modular transformation, which one rewrites the open string partition function to be the closed string partition function. And then, due to the high temperature limit, high temperature limit in this transformed basis means that this Q tilde goes to 0, and therefore one sees that the leading contribution only comes from the case when the eigenvalue of the L0 and L0 bar are 0, and this is the leading contribution. So this is the derivation of the Affleck-Ludwig-Cardy formula. Now let's add the global symmetries. Before talking about non-invertible symmetry, let's first review how does it work in the case of the invertible symmetries. Now we just need to change the partition function to be the trace over the Hilbert space with the fixed representation, alpha, which is labeled by alpha. So one thing to notice is that in order to discuss the representation in the fixed Hilbert space, in the Hilbert space with a fixed boundary condition and a fixed representation, the first thing we need to make sure is that the boundary should preserve symmetry. In other words, the symmetry operator should topologically terminate on the boundary condition. And then, in order to trace over these states in the sub-Hilbert space, it's convenient to define a projector which maps the whole entire state in the entire Hilbert space to the state in this restricted sub-Hilbert space. So, this projector is well known, and one can prove every property of this projector, such as it satisfies the standard property of the projector. So now the rest is very standard. We just insert this projector into the partition function and expand it using the formula of the projector. And then the open string channel partition function can be rewritten as the linear superposition of the charge moments weighted by the characters. And charge moment is just a partition function where we insert the symmetry operator that connects between the two boundary conditions. And then we use the standard modular transformation trick and to map the partition function to the closed string channel. And in the high temperature limit, the leading contribution is just this. And we see that the red part, the red part is the additional contribution, which comes from restricting to the fixed symmetry representation basis. And as a consistent trap, sum over all the alphas, all the representations, we reduce back to the ordinary F-like-Ludwig-Carty formula.
Can I ask a question?
Sure.
Are states M1 and M2 always known to have non-zero overlap with the vacuum?
Yes, I think so, yes. So if you expand the expression of the Carty's formula, then you'll find that there is always a zero, the vacuum component.
If you want to have a discrete spectrum, if you allow yourself to have continuous spectrum, the Q should be better.
Yeah, but everything here is discrete.
Okay, add rational theories.
Yes.
Some sense.
Okay. Yes. Yeah.
So the question is, the alpha in general can be projective, right?
Alpha is
Alpha in general can be projective, is that right?
Let me see. Well,
that's related to the fact that, for example, the Hilbert space on the strip with M1, M2 as boundary conditions could have degenerate ground states.
Well, okay, so I'm focusing on the case when
you're assuming that
the single ground state, single ground state on an interval.
So if you were to consider the more general case, then the alpha will be projective.
That's right. That's
everything.
Yes. This is important because this is important because in the derivation of these formulas, we use the fact that there is only one ground state, and this fact will also be used later in the derivation of the non-invertible symmetry case. Okay, so let me proceed to the case of the non-invertible symmetry. So we just replace the group by the general fusion category C. So again, and the boundary condition, so here we again need to put some constraints on the boundary conditions. Because recall that the boundary tube algebra, as we reviewed earlier, acts on the extended Hilbert space. So but here we want to focus on the Hilbert space where the symmetries act within a fixed, the symmetry acts within a sector with the fixed boundary conditions. Therefore, we need to restrict the boundary tube algebra to a boundary subtube algebra, where the boundary conditions are kept invariant under the action of the global symmetries. In other words, the boundary condition is weakly symmetric according to the notation in the recent paper here. Now, we proceed by following the trick that we discussed in the previous slide, namely we need to find the projector here. But in the non-invertible symmetry case, it's kind of unclear what do we mean by the character of the associated with the non-invertible symmetry and its representation. And this is where the symmetry TFT comes to help. The sandwich construction comes to help. So in order to define the projector, it's useful to introduce what is so-called the half-linking matrix, which is nicely defined and discussed in this paper. And what is the half-linking matrix? It's just a symbol, just like the generalization of the F matrix and R matrix. So it's another symbol. So what do we mean by this symbol? So we have two boundary conditions, topological boundary conditions, and there is a boundary changing operator labeled by alpha. And then we put another line, which is labeled by this purple line, which is the line in the bulk of the symmetry TFT, and topologically terminates at the two boundary conditions, x1 and x2. And the two terminations are on two sides of the boundary changing operator. And then if you look far away, it is just a point. And because we assume that the owning operator, the topological local operator, genuine topological local operator is the identity operator. Therefore, everything must be. This is just a number, and this number is just is denoted by this psi, which is an element in the half-linking matrix. Now, using this definition, it turns out that one can show this nice equality. So, what does this nice equality mean? So we start with the boundary condition, B1 and B2, with a random boundary changing condition alpha prime. And then we insert this mu operator and with the boundary condition, boundary junctions x1 and x2. And we sum over this configuration with the half-linking matrix element. And then it turns out that the result enforces the boundary changing operator to be a fixed alpha, a given alpha. So this is just like a projection operator, but this projection operator does not just act on a fixed Hilbert space on the interval, but it acts in the symmetry TFT. And in order to define the projector which acts precisely on the interval Hilbert space, we need to move all of these bulk lines and fuse them with the Dirichlet boundary condition on the left. And the result is very complicated, and it's not useful to show it here. But if we further use the modular transformation to extract the leading contribution, it turns out that everything combined together to be a very simple expression. So we again get the ordinary Affleck-Ludwig-Carty formula, and there's additional contribution. The contribution is only controlled by the quantum dimension of these boundary changing operators, topological boundary changing operators, the little m's and alphas. And also, the matrix, this capital N, is the dimension of the junction space between the three topological boundary changing operators. Okay, so we see here that the symmetry TFT, the sandwich construction really enables one to derive the formula, which otherwise it's difficult to obtain without using the sandwich construction. Okay, so let me summarize here. So in this talk, we discussed how to use the sandwich construction to label to organize the different multiplets of the boundary conditions changing operators. And it also allows us to derive this non-invertible resolution of the Affleck-Ludwig-Carty formula. And it turns out that if you use this formula, it also, and by some simple line of calculation, it also one can also derive the symmetry resolved entanglement entropy. And there are more applications which will come up here soon. For the future directions, so I would like to mention that in the last week, Christian has posted a very nice paper which presents the related idea, but not in 1+1 dimensions, but in generic higher dimensions. And he used this idea to organize the different defects of various dimensions according to the representation of the generalized symmetries. And it would be nice to find more applications in this more general setup. Okay, yeah, that's what I have. Thank you very much.
Thanks very much for this nice talk. Other questions?
So the representations of the tube algebra that this boundary Hilbert spaces have, does it completely specify the representation of the tube algebra of the bulk operators, or?
Sorry, so can you clarify your question?
Yeah, so this direct sum of Hilbert spaces that you have when you have the labels running over boundary spaces.
That's right.
We have some representation of the tube algebra on that Hilbert space, right?
That's right. But it's the interval Gilbert space, right?
Right.
Yes.
So does it fix the representation of the tube algebra that appears in the bulk local operators and bulk twisted sector operators completely?
The representation of the bulk local operators is labeled by this bulk anions, right?
Yeah.
So you are.
So in the bulk, it's a question about whether
You're asking whether the boundary conditions can completely determine the bulk symmetry, bulk TQFTs.
Right. Yeah.
Yeah, I think one can, right? I'm not quite sure.
I think maybe if you consider all the boundary conditions, no? Because
if you consider
there
all
is
the
a
boundary conditions.
bulk to boundary PE, no? But it's not an injective map, no? You lose information, right?
I see. So all the boundary conditions and the operators relating all the boundaries.
Yeah, I think so.
Okay. Thanks.
I have a question. So you had, on your last slide, you made this relation to the subleading terms and this topological entanglement and entropy. So there's this work by Salor et al., which claims that these universal corrections are actually not correct. So this is.
So I'm just making a very superficial.
I understand, but is there some more substantial relation? Because there's a debate that the subleading terms that are written just in terms of the modular S matrix are actually not correct. So Paul et al. Salur claims these are not.
Yeah, I haven't thought about that.
Okay.
That's a good question.
Any other questions? Okay, we'll get to. How about Christian? You pick this one.
Yeah, so it's kind of a follow-up to the other question, which is so the tube algebra on the boundary. That's not like the tube algebra of the bulk. It's like some tube algebra induced by the bulk tube algebra. Can you explain that a little bit?
The tube algebra on the boundary is the algebra between the open topological lines. The tube algebra on the bulk is the algebra of is the algebra of the topological lines that acts purely within the bulk, which is a circle, right? So so the boundary tube algebra will contain more information than the bulk tube algebra.
I see. So it's not strictly speaking a tube algebra. It's like something in some other type of mathematics.
Yes, I mean this is just a name, right? So we can just give them some other names.
I see. Okay, thank you.
Okay, so I think given the time, we should wrap up. Let's thank Yunqin again.
Thank you.
A coffee break. It's just outside the room until 11:15.
Sorry, maybe I didn't attract the.